Today, we're looking at source material tackling, well, maybe the biggest quest in science.
Yeah, definitely one of them. The search for a single theory, a single idea that explains the whole universe.
We've got excerpts covering the concept itself, the history behind this ambition, the, huge challenges.
And some of the main contenders, what physicists often call the theory of everything.
So our mission today is really to get into what this means. Why is it so incredibly hard to find? And what are the big ideas currently being explored?
Exactly. The core question driving all this is, can we really find one elegant way to describe everything? I mean, from the tiniest quantum particle...
All the way up to galaxy clusters. It sounds almost mythical.
It kind of is. The theory of everything, or TOE, it's often called the holy grail of physics for a reason.
Right.
Based on the stuff we read, it's about finding that one single framework, something that unifies all the basic forces, all the fundamental particles.
Like one master equation?
That's the dream, yeah. One set of principles, maybe even just one beautiful equation describing everything we see.
And this isn't a totally new idea in physics, is it? This drive to unify things.
No, absolutely not. No. Think way back. Isaac Newton. He showed the force pulling an apple down is the same force keeping the moon in orbit.
Unified Earth and the heavens, basically.
Precisely. And later you had Maxwell, James Clerk Maxwell, unified electricity and magnetism.
That's electromagnetism. Showing light was part of that.
Exactly. These were enormous steps, finding a deeper unity behind different phenomena.
But then in the 20th century, things kind of split again, didn't they?
They did. You got Einstein's general relativity, brilliant description of gravity, how space-time curves, works amazingly well for big things. Planets, stars, galaxies.
Macro scale.
Right. But at the same time, quantum mechanics emerged, describing the very weird probabilistic world of atoms and particles, the microscale.
So we ended up with this amazing theory for the very big, general relativity, and an equally amazing, if weird, theory for the very small, quantum mechanics. And the problem is...
they just don't play well together. That's the fundamental clash.
How so? Like, where does it break down?
Well, you run into serious trouble when you try to combine them in extreme situations. Think inside a black hole or right at the Big Bang. You need quantum rules and super strong gravity.
And the math goes haywire.
Completely. You try to apply quantum ideas to gravity in those spots, and the equations spit out nonsense. Infinities where you should have real answers. General relativity just breaks at those tiny, high-energy scales. And quantum mechanics doesn't really have a good description of gravity built in.
So that's the gap the theory of everything is trying to bridge, a quantum theory of gravity.
That's at the heart of it, yeah. Finding that bridge is the main goal.
Okay, huge problem. So what are the leading ideas trying to solve this? What did the sources point to?
Well, a couple of big ones stand out. First, string theory.
Heard of it. Particles aren't points, but little strings.
Kind of, yeah. Tiny vibrating strings or loops of energy. And the way they vibrate determines what particle they appear to be, an electron, a quark, whatever.
Okay.
The really appealing thing here for physicists is that the theory sort of naturally includes a particle that looks like it could be the graviton.
The particle that carries gravity.
Exactly. So it might automatically incorporate gravity into the quantum picture, which is a huge plus.
Interesting. What's the other main approach mentioned?
The other big contender is loop quantum gravity. It takes a different tack.
How so?
Instead of starting with particles, it tries to quantize space-time itself. It suggests maybe space and time aren't smooth, but are actually made of tiny discrete chunks or loops at the very smallest scale.
So space itself is grainy.
That's the idea. And importantly, it tries to do this without needing extra dimensions like string theory often does. It's building a quantum picture of gravity from space-time structure up.
Wow, okay. Two really different pictures. String theory and loop quantum gravity. But neither is proven, right? That's the catch.
That is absolutely the catch. It's why there's still theoretical frameworks, really hypotheses.
And why is proof so hard to come by?
That's the massive hurdle.
Yeah.
The energy levels you'd need to, say, directly see a string vibrating or detect the granularity of space proposed by loop quantum gravity, they are just colossal.
Way beyond our current particle accelerators.
Way beyond. We're talking energies that likely only existed fractions of a second after the Big Bang. Or maybe near black holes. Extremely hard to access experimentally.
So you can't just build a machine to test it easily?
Not right now, no. We look for indirect evidence, maybe cosmological signatures, but direct proof is elusive.
You know, reading through the material, it felt like this search is about more than just tidying up the equations, it called it a profound exploration.
I think that's right. Yes, it's about unifying forces and particles. But the quest for a toe digs deeper. It's fundamentally asking why the universe is the way it is.
Why these specific laws? Why these particles?
Exactly. If we found it, it might tell us about the true nature of space, time, matter, energy at their most basic level. It taps into that deep human desire, to understand the fundamental logic of existence.
To find the underlying simplicity.
Yeah. Is there an ultimate simplicity behind all this complexity?
So we've gone from those early unifications like Newton and Maxwell through to this modern standoff between gravity and the quantum world.
Yeah, and looked at these really ambitious ideas like string theory and loop quantum gravity, trying to find that single, hopefully elegant truth.
It's quite a journey.
It really is. And it leaves us, and leaves you, the listener, with a pretty mind-bending thought to ponder.
Go on.
If we actually did find it someday, if we discovered this theory of everything, this single framework,
Yeah.
what would that really change? How would it shift our fundamental understanding, not just the cosmos, but of ourselves and, well, our place in it all?